All right.
Yes, I do.
There. Phew. That was painful. All right. All right. Got a lot to cover today. Let's get started a minute early. Ladies and gentlemen, welcome to Risk 5 Datapath Part 2. Woo! Happy Friday to you all. Thank God it's Friday. I love it. All right. I'm sure you're all thinking about the midterm. The midterm is this coming Monday evening. We'll talk more about it on Monday, but you're hopefully going to be working with a team of folks to study together. Do not study alone. Study with a team of folks, pull out old exams, kind of exams that have ever been done in the last kind of N years. We have a whole exams page, and push each other. Make a new problem. Oh, hey, here's a bit representation. Convert it to, sign magnitude or something. Play with different things. Look at old questions. Have some fun. Teach each other. Create a learning community. We love that. We much prefer having students work together when they're studying rather than work alone. I always have students every year. I've been doing this for a lot of years, teaching at Cal for 33 years. Students say, Dan, I bombed the midterm. What did I do differently? I always say, did you study alone? They always say, yup. That's it. People who don't do well, there's a high correlation with those who study alone. So please do study together in a team. Look at all the lecture notes, the labs, the projects. Perfect. All right. There's a lot to cover. There's a lot of things that we have an exam. It's really, Pam and I have been working on the exam with an amazing group of teams. By the way, our staff this year, usually we have a great staff, but this year in particular, we have an amazing staff, and we're working and polishing that. We're honing all the rough edges of the exam to try to make it something that's really we're proud of. So hopefully you'll all be proud of it as well. It's a good exam. All right. So where are we? Big picture. We are trying to build a machine. We are trying to build a CPU that will run and execute our RISC-V machine code that we have compiled, assembled, and linked down to. So what we've seen so far is this. We have a working machine for add, sub, and add-I. That's amazing. And this is what we had. People were asking me at the end of the lecture, like, when does the write actually happen? This is an edge-triggered write. All the writes happen on the rising edge of the clock, and they follow immediately after. So that data W, is sitting on with the value that you just calculated for the add, and it's sitting there on data W, held stable by this ALU. It's held stable. Everybody's stable, 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 and then rising edge of the clock. So it's stable well before T setup, and it's going to be stable through T hold so that it writes after that. So rising edge goes down, and then rising edge again, it writes at the end of the day in that sense, okay? So we're going to try to implement the rest of all of it. This is amazing. In one lecture, we're going to cover everything other than adds, subs, and add-I, which is all of this. So it's a big lecture. We're kind of going to go fast, but you've seen the big ideas, which is we got a new instruction. The data path we have doesn't handle that instruction. How do we add a wire to make it happen? So that's all we go doing is basically expanding this picture with more wires and more muxes to do more things that we do. That's today's lecture. And we're going to kind of go through in a burst. It's kind of fun. All right, loads. This is a load. Let's go through this. A load is really very close to an add-I. Why is that? Because I'm reading from a register. Let's look. What is the semantics of this load? You see down here. Here is the semantics of the load, right? What does it say here? Here. Reg file R of RS, load from. Store to, load from. So we are going to be reading reg of RS. So we didn't have any memory before. We only had ALUs and the register file. We're going to be reading from reg of RS1. Let's go show you what that is. We're going to be adding it to the immediate, and we need to then store that value in a register. That's the goal. So let me make sure I cover everything here. The address is the base address x2. It has to be added to the immediate x1. That's the offset. Remember that? So I need to be able to, wait, read from a register and add to an immediate. That's what we did in add-I. Read a register, add to immediate. So we already have the machinery to take a register's read value and add it to immediate. That's why we cover loads next, because basically the add-I's did most of that work. All we have to do is, don't forget, at the end of the day, read from the register and then store it back, read from memory and store it back in the register at the end of the day. So there's our register block, DMEM. If you recall, we separate IMEM, a read-only device, which is poking down at the code part, down here at the code part of my memory area, only read-only, combination of logic, no clock into it. DMEM, clocked, but because we're only reading from it, the clock isn't relevant. That also was treated as combination of logic. We're just reading it. The moment that there's a valid address, after some delay that happens with naturally every single block, we're going to be able to have that data at that memory address there. Now, before we were only writing directly from the ALU to the register input data W. Now we're going to be reading from DMEM. And so when we have two guys that want to drive one line, what do we use? A MUX. All right, everybody online say MUX, which means we have to introduce a new MUX. So that MUX is going to determine, it's a flag person determining, hey, who gets to drive data W? Is it the ALU, which is the 0, or is it memory, which is the 1, okay? So we're going to have a new control line. All of a sudden, our control's getting more complicated because we have to think about more things the marionette has to control. Here, the marionette's in the bottom, kind of reverse gravity, controlling from above. So mem, read, write, we are certainly not writing to memory, so that's going to be set to read only. And we're going to set write back select to 0, which means we're getting it from the memory, okay? All right, so here we go. New instruction. PC gets set up, comes out, goes through PC plus 4 because the following instruction is PC plus 4, so that's waiting on the input out for the next clock cycle. We fire out, we do the instruction fetch. That's the next, this is all the same stage, instruction fetch. It means new PC, and get this. That's the first stage. We're going to take the 32 bits of that, send it to the registers that are going to be used. Not all of them are going to be used. If you might imagine, R of RS2 is not being used. Why? Because we are taking the B input to the ALU is getting input from the immediate generator, not from the register file. So yes, there are bits going into R of RS2, 5 bits going in. It's acting like a combination logic block. Data R2 has the value. It's being ignored by the MUX at the end that drives the B input to the ALU. We saw how to do the immediate selector, We know how to do that. We already know how to do this. We take these 12 bits, we make them 32 bits. Reg write enable is 1. Yes, we better be writing to the register at the end of the load word. B select, which is who drives the B input of ALU, maybe I use my cursor so you can see, is definitely a 1 because I'm getting from the immediate. We also sometimes write immediate here rather than 1, so you don't have to worry about it's 1 or 0, just write immediate. ALU select is add because I'm adding that in the semantics of that. Mem read write is read. I better not be changing memory on this operation. And who gets to drive back, write back select? It's 0, which means it's coming from the memory, okay? So ALU calculates the offset plus the immediate. So this is the third stage. The third stage. Second stage is register read. This is called the instruction decode. Instruction fetch is the first one. Instruction decode means read registers and calculate the control. Execute the third stage does the addition of the offset plus the immediate. Memory is the fourth stage. Yes, you are doing a read of that memory, which is great. And bloop, and see this ALU, they're both purple, but you're only actually using one of them because the MUX is going to choose only one of them. And the fifth stage, we call it the write back stage, is writing back to the data W, and that factors in T setup as we talked about before. Isn't that awesome? So load word wasn't much harder. We added one MUX and we're done. That's awesome. We can now add one. So it's kind of the question is, as we continue to add instructions, how much more work is it? That wasn't much more work. Just add another MUX and we're cool. Well, I got to put the memory block in there too, but that's kind of cool. All right. Now, we have different register widths, okay? You remember this load byte, load half word. You take the top bit on a load byte, you smear it to do all that. We're going to assume that the memory block is kind of wrapped in a meta node that'll handle all of that. So we'll just assume that if you ask for a load byte, the memory block does the right thing and has the right values on the upper bits if it's less than a load word. So don't worry about that. All that sign or zero extended is going to be handled by the memory block. It's a little thing you have to build, but we'll assume it does it for it. We kind of sweep it under the rug, if you will. All right, stores. Basically the same syntax, just semantically different for a store word. Store to, load from. I'm storing to memory. Here we go. So a store word. What's weird about a store word that you saw, and we were kind of annoyed with, but we understand why, is this immediate is weird. Like 11 to 5 and 4 to 0, it's kind of different. It's kind of weird because we're going to try to keep the register positions in the same spot. You're going to thank me when you're wiring this together that these are all R1, RS1, and RS2 are exactly the same spot. Why? Because I'm reading from two registers. Like an add, like an R-type, I read from two registers. So literally lock those in. Well, I got to have 12 bits of an immediate for the offset. I already had the top 12 bits here, 11 to 5. Let's stuff them over here in RD because the goal of this is not to store into RD, but to store into memory. Store to, load from, which is why, if you remember, we push the immediate 5 bits over there. So we have to now somehow be able to wire that across. The semantics are below. Register is going to be reading in RS1 and reading in RS2. This is cool, actually. The first is the base address. That's exactly the same as the load word. R of RS1 contains the base address. It's like the A. If I have an array, it's that A. This immediate is the offset, A of 40. That's the 40. You're going to add to that. Now, R of RS2 is the value to store. I'm storing the value in RS2 into the address pointed to by RS1 plus the immediate. And again, PC equals PC plus 4. So this immediate selector, we got to put those bits in a different place. They don't come in the same place. Before, the immediate for I was all 12 bits consecutively on the left side. Remember that? It was all those 12 bits, and we do something for that. Here, the bits are now switched. So this immediate selector has to be a little bit more clever. To do that, I have a next slide to talk about that. Now, this is the first time we've talked about writing to memory. In fact, only the stores write to memory. Only S blank writes to memory. So now this is the first time we've ever used the data write input on the memory block. If you look over here, data W had been not used. Now I care about the fact that it's a clock device. Now I care about T setup for that memory device. So I've got to figure out how it gets that. Oh, over here, the value is on data of R2. Do I need a mux there? I don't. It's the values used two different places. That B, the output of data RS2, goes into the mux because sometimes it's added to, in the case of like register and add. And add, that value is the actual second register to add. In this one, this is the value to store. So this just goes around that mux, takes a side road, and goes into data W. You don't need a mux for that. So whenever you split it, you don't need a mux. When you have 2 to 1, you need a mux. 1 to 2, you just split it like that. Many of these lines are split. All those circles mean you're just splitting them, okay? The only thing that's super different here is immediate select is different because those bits come from different places for the immediate. We just saw that. They're not 12 consecutive ones. They're split into different places. So this got to be clever about that. And holy moly, it's important that I change memory rewrite to be write. If that's read, that store does nothing, obviously. So we have to set that to write to do that. But nothing else really changed. Look, I changed the InGen to put in an S, so magically it handles the S. And I got to wire this around to data W. So that was pretty easy to add. I didn't even need a mux. I just had to make sure that my control, again, going to be complicated, had to change memory write to write. That's it. Great. So how does the immediate selector work? Let's actually go that in the next a couple slides. I have a clicker question, which is, what are the control lines for reg write enable, B select, and write back select? I've talked about the other ones, but I haven't talked about these guys. So let's talk about what those three things are. Reg write enable. What's this one set to? That's the first one. What is B select? What is this guy set to? And what is write back select? What is this mux set to? Ready? Go. Okay, and I'll click this button, and we have a little interactive peer instruction, peer learning here. Go. And by the way, this lecture might feel fast. It is because we're trying to cover all of it at once, but really we're only making small changes. You know, add a mux here. Okay, now I can handle that set of instructions. Modify the immediate generator. Now I can add more instructions. I'm supposed to click this button. I'm supposed to click this one so you can't see each other's values. Okay, here we go. I got 2 people. Let's go some below. I need value of 3 different bits. Reg write enabled, B select, write back select. That's A, whether you're writing or reading to a register. Are you asserting that? Are you writing to that? B select is 0, 1, which one drives that mux, and write back select. By the way, if you've seen those SCL, it's very clever. Select means like, which are you selecting from? It's a mux. It's how you're driving that. Reg write enable usually means 1 means I'm writing to it, 0 means I'm reading from it. Although most of the time we try to have just R or W, not a 1 or a 0, but here we're saying, are you writing to it? Are you turning on write enable? So 1 here means write is on, okay? Are you enabling a write? All right, I got 20 people. Let's see how you did. Okay, most people are 010. Let's take a look at the answer. So let's light this store path. Here we go. Increment. I didn't tell you the answer yet. PC to next instruction. That's the same thing. Set up this is instruction decode still. Set those values, those bits into the register because I need to read at least 2 registers there. Set 12 of those bits over to, 12 of those bits over to ImGen. Let it do its work. Actually, it's more bits that go into ImGen. 31 to 20, this has to be modified. That's actually a bug on that slide. That has to be more bits because the bits come from different places there. Store does its work. I see ImGen is SL. Reg write enabled. Do we write to register now or not? No. I read from, I'm going to write enable. Store 2, my goal is to change memory. This better be 0. The first bit better be 0. Reg write enable. B select, I'm clearly choosing from the immediate path here, just like I was loading a store. That's a 1, so I should have 0, 1. How about this write back select, though? That's a little weird. I love this question. So this data gets passed. R of R2 comes out here. That's the data to store in purple. That comes in here, fits in right to the data W line. Bloop, okay? This address comes in, which is the calculation. It's kind of cool that in cyan, the address to write to is like, all of this is getting very excited. This whole line is like lighting up. The base address is the top cyan line. The bottom cyan line is the immediate. You add them together with the ALU, that's the player you're storing to. Hi, Mr. Memory. Cyan is where I'm storing to. The purple is what I'm storing. Bloop, and I plug both of them in. Now, that purple line goes to here. There's some output of that memory device. It's also being served as a read device. It's always active, and that is being served always, universally, all the time as a combinational logic read device. So whatever used to be at that address is now on the purple line on the output right here. But guess what? And by the way, who gets to choose? Is it from here or is it from the ALU? That's the question for you. Don't matter. Why? Why does it matter who gets to drive this top line? Why does it matter who gets to drive this top line? Because it's not bold. Why is it not bold? Because this is a 0. When reg write enable is 0, I'm not writing to the register. So I don't care what line happens to be feeding data W because it's not being looked at. Does that make sense? So we call it a don't care. In the logic gates, you write an X or a star. That means you can optimize your logic. Rather than trying to optimize logic for one of these 2 cases, maybe it might make sense to always set it to 0 or always set it to 1. So I basically let the logic optimizer look at that and say, hey, this doesn't matter. So as you're doing your Boolean logic simplification, whichever would make your equation smaller, fewer transistors, choose that. Because that doesn't matter to me. So whether it's always a 0 or always a 1, one of those 2 is going to be true. I don't care. Whatever your equation is, I don't care because your logic now can be simpler. Isn't that cool? That don't care is really important when you're doing logic optimization. Your Boolean algebra, I would love, let's make sure we have that on the midterm and final, to have an X in there so you can make a decision. Now, I don't care. Make the simpler one of the 2. You can play with it. Is it better to have it a 0? Better to have a 1? Maybe it's just like, A or B if it's a 0. Maybe it's a complicated thing, it's a 1. So make it simpler, A or B. There's only one gate, an OR. Isn't that cool? So do that. Isn't that kind of fun? I really love that don't cares because you can look at that for your logic simplification. Okay. B types. So we're trying to cover all these in the time. I'm doing pretty well for time, but I feel like this is a rush lecture. There's a lot of slides. I think it's like 40 slides. Normally it's 24. Okay. Branches. Again, there's a lot of pictures, but nothing, like what's the new thing? Well, Dan, you told me I had to modify the immediate guy. Yep, we did that. We had to modify and add a mux over here. That's all we're doing. One by one, we're just modifying and adding small things at a time to what you already understand pretty well, I hope. Okay, I got a new immediate format. What do you mean? Remember these branches? Branches are weird. You remember the whole story behind the branches? You want to count by half words. You want to be as consistent as you can to most of the bits from the other one. So we saw that before. So we had this weird format that what is that about? And now you understand why. We had a whole lecture on that when we did this. Reg file, I'm reading from 2 registers because I am, this is the branch. I'm a branch says read from two registers, and if they're the same, take the branch. If they're not, if it's a branch equal, do something else, okay? So the PC equals either is PC plus 4, which means you didn't take the branch, or PC plus the immediate, which means you did take the branch. All of a sudden, you're going, wait, uh-oh. We have never had to add a PC plus an immediate before. We added a register R of RS1 plus the immediate. We never added a PC. So all of a sudden you're thinking, oh, how do I now stuff the PC as another possible guide to A as the first thing, as the top thing of the mux to add? You're like, oh, I need a mux for that. So you're already knowing how to do this. And by the way, on exams, we say, hey, implement this new instruction that doesn't work with the current thing. You're like, how do I make it work? Oh, add a mux here, add a mux there. That's what you're doing. The same thing when I'm talking you through, that's what you'll do on an exam. So PC, and by the way, the PC isn't always hard-coded to PC plus 4. So what do we put over here? We got to figure out what to put over here. What do we think we need? 1, 2, 3? A mux, because sometimes it's plus 4, sometimes it's from this magical PC plus the immediate. But we also don't know how to add the PC plus the immediate. So PC plus 4 is handled, okay? Now, I'll make sure I read everything it says, just so I know that. Here's the problem. This ALU, I've got it. So this is an adder, okay? This is an adder that takes, hey, that's plus. PC plus immediate. This ALU is going to be used for the plus. See the PC plus immediate? That's what it's going to be used for. But I also have to compare the value of the two registers and see if they're the same. This box could do a comparison for me, but I can't do two at one time. Does that make sense? In one clock cycle, single cycle CPU, that box is doing one calculation. The bits to do are solid. It's not like, well, first start by doing this one, then switch it. No, it's locked in for that whole clock cycle to do one operation. What do you want it to do, Dan? You're asking me to do two things. One, add an immediate to a PC. We can do that with the mux to throw the PC in there on the A line. And to compare reg of RS1 and reg of RS2 to see if they're the same. I can't do both. That makes sense? I'm trying to argue and motivate that. So we introduce the branch comparator, which is a new box, pretty small, pretty lightweight. It's not that hard to build. That's going to be comparing the values coming out of R of RS1, which is data R1, and R of RS2, which is data R2. You compare them, you make some decisions. Well, here's the question. Sometimes you're doing a less than, branch BLT, branch on less than. Well, then I need to know whether the things I'm doing is an unsigned value or not. Remember that I talked about before? I remember standing right here going, all zeros and all ones. Zeros are less than all ones when it's unsigned. Zeros are bigger than all ones when it's signed, because all ones is -1. Right? So I need to know whether it's a signed or unsigned comparative only for the less thans, not for the equals, but only for the less thans or greater than equal guys. So what I get out of this box is a cool box. I tell it whether you're doing a comparison, whatever comparison you're doing, unsigned or not. I get two more data values input to my control. They are branch if equal or branch if less than. Not branch if. Is the branch equal or is the branch less than? And now I can do all these cool things with that. I can take those two values and do all the things. I now know all that I need to know about these numbers. Just give me those 2 bits. Are they equal on one line? Are they less than on the other line? It's pretty cool, actually. Okay? So this is 2 more bits that the control line, the control box at the bottom, mission control, is going to be using. Now, I need to introduce a mux over here on the left. You kind of knew that was coming. We knew that was coming to tell me, is it the +4 or is it this magic PC plus immediate? We haven't built that yet. So I got an ALU that's going to be doing my plus. First of all, let's take a look at this. This branch comparator is a combinational logic box. It's pretty cool. Let's do it. Input is 2 data buses, the 2 registers, R of RS1 and R of RS2. We talked about that. It's also whether it's unsigned or not. The output is either branch if equal, that's pretty easy, 1 if they're the same, and branch less than if A is less than B. So the control logic says set branch of unsigned based on the current instruction. Is your branch an unsigned comparator? Then I set that high, that's easy. Set PC select based on the value of branch equal or branch less than depending on the particular instruction. Again, more control logic to make decisions like that, okay? So PC select, I'm going to be telling it, hey, what's the next PC? This tells me the whole instruction, so I can look at all the bits and find out what the bits of all the what flavor of branch is. That's what flavor of branch comes in these set of bits. This tells me whether those guys are equal or less than. For example, let's do it. If branch less than is 1 and branch equal is 0, then what do I know? If, by the way, if you do a BLT, which I'm getting hungry for lunch already, you say branch on less than. Okay, I did that. And you have to set it whether it's unsigned or signed. This in particular is a signed comparison because it's not BLTU. And I get BLT less than is 1, equal is 0. What do we know? It's less than. It's less than and not equal, therefore it's less than. That makes sense, not too hard. So then I set it to taken, which means I take the branch, okay? Oh, how about this? BGE, branch greater than equal. Well, no, A greater than equal to B is the same as A less than B not. Isn't that cool? It's not less than, therefore it's greater than or equal. So that means if BLT is 0, which means it's not less than, just think of the logic. If it's not less than, it's greater than or equal. So if BLT is 0, then that means, hey, it is greater than or equal to. And it was branch and greater than or equal to, then I say taken, and I take that. Make sense? It's kind of cool. All right. So now, only thing missing is how do we add a PC plus an immediate? Remember, whenever you need to take a value and split it multiple ways, you just put a little circle here. I can show you the circle on Zoom. You can see it. I put a little circle here, and then you send it to wherever it needs to go. Where's it going? To the ALU. Wait, the ALU already has somebody sticking into the A thing. That's from the register file. What do you need when you have two guys need to drive one output? A mux, right? This is our word of the day is mux. You get $1 for every time you say the word mux. All right. So this comes over, and it's a 1 and a 0, and when it's a 0, it comes in from the old R of RS1. When it's a 1, it comes in from the PC. And now the ALU's output is PC plus immediate. And now you're going to worry, wait, that value has to go all the way back. Look, in cyan, this beautiful line has to go all the way back and plug into the other side of that mux to tell you what the future PC is. Are you the PC that came from stage 3, or are you the PC when the PC plus 4 that was already ready for you a long time ago? Because the plus 4 is very easy to calculate. Okay? It's a lot to do. Question in front. Yeah, very fast. Which generator's output? The branch comparator. Yeah, the branch comparator, this goes to control. These two lines come to control. Yeah. Yep. You can see it on the picture. Yep. So control gets all the other lines it has. Look at all the arrows. It gets the full 32 bits of instruction to know, ooh, what's func 3, what's func 7, what opcode am I doing? It has the two inputs from branch equal and branch less than. Every other line that touches control is a line that control is marionetting, controlling the system. So the inputs are so far only those two plus all of the inputs on the instruction line, where you're going to be looking at the opcode and func 3 maybe, and func 7 maybe if those exist. Okay, good question. All right, so light in the branch data path. That PC comes out. It goes to the plus 4. It goes over there to the mux. Hopefully this plus immediate comes in. This is a branch using a weird branch. It comes through. Are you writing to register? No. Turn that to 0. Writing to memory? No. Turn that to read or 0. You set the branch unsigned depending on whether your branch is an unsigned or signed comparison. You set B select and A select to 1. So 1 means the new guys. Like 0 is the old guys, 1's the new guys. So the new guy on the top on the A line is the PC. The new guy on the bottom side is the immediate. That's two new guys. The old guys were register values. Now they're the new guys, PC plus immediate. That comes in. Memory write read, better be read. You better not change the memory on this guy. Better not change the register file on this guy. Everybody changes one state element. The guy who's most important here is the PC. That's all the guy who changes here, okay? Write back select, do we care? No, because we're not writing to the register, so who cares what the input on the data write line is? Exactly right, okay? And I'd put this here, but this is all fast. All the same thing, okay? And you make a decision. At the end of the day, some control logic is doing a lot of work. Look up the table, use those values, and decide what PC select is, and then PC gets a new value on the next clock cycle, and you either take the branch or don't. That's the magic of how branches get taken or not taken. All that work was to make those decisions. Super cool. Just combinational logic. Don't write to memory, don't write to registers. I don't care for those values. I love it. Okay, immediate generator. We kind of swept under the rug how to write the immediate generator. So here's how to write imgen. I have so far two guys, an I-type instruction and an S-type. They differ. By the way, you're welcome for trying to keep the immediate fields the same spot. Now you're like, why did you keep them and why did you split them in weird ways? Look, the top the top 7 bits are the same spot for both immediates. That's kind of cool. So here we go. Let's take the bits up top. Let's stuff them here. So here, the sign bit for both of them is the top bit. Notice the bit, this is a 12-bit immediate for both of these guys. The top bit of a 12-bit is 11th bit. So that sign gets smeared to here for both of these operations. The only problem is, see the cyan guy, the blue guy? They come in different places. What do you do when two different people want to drive the same line? Use a mux. You get another $1. Cha-ching. And by the way, for now, instruction 31 goes to space 11, and you just smear it across for there. And I got to muxify, wait, right here, I got to muxify those guys. Bloop, there's my mux. And what's it driven by? Is it an I-type or an S-type? And so actually, I like ImSelect to be S or I. I don't like zeros and ones here. I actually like to give it a letter, so I know which one I'm playing with, which makes sense. That's all we got to worry about here. It's pretty cool, right? That's not too bad. And you're welcome for keeping everything mostly in the same spot, right? You only had to do one mux. Uh-oh, this B-type is so annoying. Look what I did. But let's remember, we tried to do as much as I could to keep the B-type guy the same, which is, look at the sign bit. It's still, now I'm looking at, I stored 11 bits, but it's like shifted over by one because I'm counting by half words. But the top bit, the 12, is still the sign bit. So that's the same. That's why I did that 12. That's why, like, why would you do that, Dan? Everybody's like, why do you do that? This is right now, this is the answer to the question you asked about a week and a half ago. This is always the sign bit. So now, what happens at bit 11? Well, sometimes bit 11 is the top 2 bits in the I-type. Sometimes it's the 10th bit in the B-type. So, whoops. So this has to be a mux, which is that the 11th bit was actually over bit 7. So the 11th bit comes from here in the B-type. It comes from the top, from bit 31 in the I and S-type. That's easy. This lowest bit has to be a 0 for bytes. Why? Because you're counting by half words. That's always going to be a 0. So sometimes, you just mux that in. That lowest bit is a 1-bit mux. Sometimes it's a 0 when it's a B-type, and sometimes it's whatever the bit was, which is stored in field 7, I believe, in the other 2 types. But that's it. Just got 2 1-bit muxes, and I got the rest of it done. Isn't that cool? So that's actually pretty neat that most of it we keep the same. And look, 4 to 0, 4 to 1, 4 to 1, the same as S and B. So that actually bits stay the same. If you look over here, see these? Look, 4 to 1, 4 to 1. Aside from the rightmost bit, the rest of the other bits, the rest of the 4 bits are the same. So those bits come in here and flow right in there, which is kind of cool. So mostly we have the same. We just got to do a little bit of 1-bit guys here and something strange about, so we only had to introduce, to do B types, a 1-bit mux here and a 1-bit mux there. The rest is the same. That's awesome. That was clever design. 2 1-bit muxes, we built it together. We literally built it together, a 1-bit mux. And now you don't do that. Now you can handle a B type. Makes sense. All right. Well, we're doing great for time, by the way, folks. This is wonderful. All right. JAL and JAL-R, those are a little bit harder. Let's play with that. Phew. Okay, what's the semantics of JAL and JAL-R? Well, let's look at what is JAL. It's like jump and link, right? You're making a call. Remember, it's link and jump. Whenever you see JAL, you think, oh, it's link first and jump. What does it mean? Link says, set R of RD to be the current PC plus 4, which means whatever instruction you're on, so that after I make this function call, the next guy I better store somewhere, so I know how to get back. Once I make a function call, I move the PC, I gotta know what the next line was to come back. If you ever wondered, like, how does it remember? Literally right here is how you knew how to come back. Because you're gonna store, hopefully into RA, the guy that it could be someplace else also, but RA typically is the guy you're storing into. So PC plus 4, wherever I am, plus 4 is where I come back to after I make the function call. Make a function call, do the foo, come back to here. I gotta store that somewhere. So that happens first, link first. R of RD gets PC plus 4. Then you take the jump, and it's a PC relative jump, which means PC plus immediate. We already have machinery for PC plus immediate. We just did that. So this is actually not that bad. The only thing that we don't have to have is we haven't ever changed a PC and change a register. So let's actually take a look at how to do that. But again, not hard. What's the type? What's the type for JAL? It's a normal immediate. It's a boring immediate. So that's just an I type. If you remember, that was an immediate type format for JAL. By the way, if you ever forget, it's on the table. Look in your answer sheet, the green sheet, it'll say JAL, JAL-R. It's an I type. That's how you know how to do it. Here's the problem. We had never stored R of RD. Up to right now, whoever drove the register, R of RD, the register gets written at the end of the day, was only ever driven from the ALU, right, in an R type, or from memory in a load word. That's all. We had never driven it from a PC plus 4. Do we need the ALU for the PC plus 4? Well, we kind of have PC plus 4 already over here. We don't need to pass an ALU in here because I can't. This ALU is already computing PC plus immediate. It can't also do PC plus 4. Well, how do I get PC plus 4? I got a box over here called PC plus 4. This box is PC plus 4. I've been using it forever in the R types. So take that value, stuff it into this mux. Why? This mux is the write-back mux. That's the guy that determines who stores data back in the register in the end of the clock cycle. So I just take it from a 2-input mux to a 3-input mux. How do I build a 3-input mux? I cascade. I need 2 bits, right? But I cascade 2-input muxes like this. These 2 win the first battle. The winner plays, like you get a bye. Remember how we did the 4-to-1? We had like a tournament. These 2-to-1 muxes feed into the next 2-to-1 mux. Now you just need 2 muxes. These 2-to-1 is like the first round. Then this one gets passed into the next one, and then that goes in there. It's very easy. You want me to draw that? I'll draw it just really fast. I have 1 minute. I'll draw this picture. Pen, white. So here's a mux. Here's this mux. It's 2-to-1. Boop, boop. Here's the third guy. Here's another mux. It just gets the winner of this and that. And there's my 3-input mux, 3-to-1 mux. You just need 2 of these 2-to-1 muxes. You can make it work. And like a tournament, the top team kind of got a bye to the next round. This is exactly like we did before. That's not so magical. And this somehow encodes the 2 bits, what I would encode that. By the way, this value is only ever 0, 1, and 2. We're never letting that be a 3. It's only ever 0, 1, and 2 for that, because that's all we'll ever use it for. That was it. All I had to do was kind of make that 2-input mux a 3-input mux, and I'm done. Literally, I'm done. That was super cool for this JAL-R. The rest of the machinery kind of worked. We're kind of building something like, wow, it already does it. It already does 90% of what we need to do. How do you do PC plus immediate? We just did that. We just did the PC plus immediate. Just make that work. Super cool. So let's light it up. Let's fire it up. Comes in. PC gets sent to the add plus 4 box. That plus 4 is not going to be immediately sent back in here. Let's do it. Why? Because PC is always PC plus immediate, which means the value of this guy, the value of PC plus immediate here, this one, you're going to see is the one that drives that. It's always going to be set to that. Let's do it. Okay. Generate the byte offset. We got to do a byte offset for this, for that immediate. Okay, so that's an I type. That's an I type. Reg-read enabled. Yes, we are internally changing the register. Look at the semantics. We're changing the register there. That passes into this immediate generator. PC plus immediate has to be passed in to the ALU. So the ALU says 1 and 1, just like it did before. Just like before, the PC plus immediate, it's doing that here. It computes it. It stores it back. This is saying always taken. This isn't a question mark. We're not asking. I'm not asking you, should I branch? Should I not branch? That's a J, folks. I'm taking an unconditional branch. This is hard-coded to a 1. We are taking that branch. It's not like, well, should I take it or not? No, we take it. That's what unconditional means. You got to take it. ALU select is add. A and B are 1s to take the outputs, the inputs to the ALU from the PC, which is the one there on the A line, and the immediate, which is the one on the B line. Memory rewrite. Should we check that to write or read? There's no, look at the semantics, top right. There's no memory in there. So that better be read. It does serve as a read-only device. It calculates some value. Output of data R is some value. That mux goes, thanks so much for your value. I don't need you. The output of the ALU is sent in, some calculation. That's some, that's PC plus immediate, but it's not used. It's used with the line that goes back to write to the next PC. That ALU is, sorry, don't need you. What it does need is it needs PC plus 4. And that's the guy that gets driven. So right back select is 2, otherwise known as PC plus 4, and you're done. Isn't that cool? Not too bad. So JALRs are really not that bad. I think I didn't have to add anything to this, to be honest. We just had it. We just had to wire it through. I guess I had to make it a 2 to 3 ALU. That was it. Pretty simple add. And stage 5, write PC plus 4 to this register. Remember, the last stage is write back to whom? Write back to the register file. That's what that does. And who gets updated at at the end of that day? This register file gets a new value. Look right here. Look at the semantics. The register gets a new value, and the PC gets a new value. Okay? And by the way, we don't care what these values are. I'm not even using this branch comparator. So pass a star in for the branch unsigned, because I'm not even using that branch box. So put a star, because let the logic be more optimized for whatever makes sense for that logic. Pretty cool. All right. JALR, almost the same as JAL, but what does JALR do? What are the semantics? PC equals R of RS plus immediate. This is a little different. This is the one that's like explodes. Boy, I don't know how far I can jump my PC, Dan. Look at my slide. My PC can only change by as much as a 12-bit immediate. That's as far as it can go. That's not very far. I mean, 12-bit immediate, what's that number? 2 to the 11th minus 2 to the 11th. 2 to the 11th is only 2,000. That's only 2,000 different values, okay? So, 12-bit immediate is 4,000-ish different values, mostly. But I want to go anywhere. I'd like to go anywhere. So wouldn't it be cool if I could have any 32-bit value in a register, and even on top of that, add an immediate to it? Like, that's literally anywhere. That's anywhere, anywhere, anywhere. Those bits could be any fit, and that immediate even goes to places relative to that, which is kind of fun. You almost don't need the immediate, but it's kind of nice to be able to have it if you want to be able to keep the same register and then move different places around it, I guess. And R of RD needs PC plus 4. So we mostly have, I think, all of this done. Let's do it together. By the way, this is called absolute addressing, not PC relative, because PC has no argument for the input for the old PC. It's not relative to the old PC, it's relative to the absolute value in this register, offset by some little bit of number that you can change and play with that. Okay? It's I format. Hey, we love it. Same format. We can just use the I format for the immediate generator. That's awesome. That's perfect. Okay? So let's line it up. It's like nothing I need to change. And nothing to change. We just got to line it up differently. So PC comes in, all of the instruction fetch. Now I'm decoding the here in the red. This is the instruction. The second stage, instruction decode. Those values go into here. Why? Because I'm reading R of RS1, so that better fire hot. I am going to be writing to RD, so that fires hot. I'm not using R of RS2. Does that mean 5 bits still plug in? Yes. Does that mean that still acts as a combinational logic device? Yes. Does that mean some data is on data R2? Yes. Does that mean it's going to be used? No. Doesn't matter what it is. All that before. You've seen all kind of that same story before. ImGen we saw is an I. Reg-write enable, what do you think? Look at the semantics. Am I writing to register? Yes. Put that to 1. Better be changing a register. Am I using the branch comparator? No. Make that a star. How am I feeding my ALU? I'm feeding it from the immediate, so that's set to 1 down here. And 0, look, 0. Look, this is the 0 because the 0 says take it from the original guy. Take it from this guy right here, okay? That's the cyan guy. So that's a 0. 1 says from the immediate. That's now R of RS1 plus the immediate. Mem read write is read. Write back select is 2. Why 2? Because PC plus 4 comes around to be R of RD. We already kind of had that ready for that. And so I said this to be PC plus 4. There's PC plus 4. And I'm going to throw that in R of RD. So what's funny about this? I'm going to say, what I feel like, and this is just me, I don't think this is actually how it happened. I feel like somebody said, you know, if we wanted to, we can make an operation that can do that semantic of the top 2 lines up there because we already have it wired to do all those things. I don't think that's how it happened. It'd be kind of funny if like somebody said, hey, you could do this. Let's make a new instruction because it costs us nothing. Here's what I'm saying. The risk philosophy is don't add a new instruction because it makes me do more work. But the existing hardware already does that based on the other things we needed to support. So why not give them one more instruction that costs me 0 more hardware? The whole risk philosophy is no more hardware, minimal hardware. Hardware already does it. So why not give them another instruction that you can use at the top compiler level because I didn't have to buy any more hardware because my hardware already does all the things I need to do. Can I read from a register? And add to immediate? Yes, that's like an add I. Can I stuff it into a PC? Yeah, that's like we did that before where I add to a PC. Can I take a PC plus 4 and stuff it in the register? Yeah, I did that already. So I basically don't need to do anything different. Nothing new for this instruction, and we can support it. It's kind of funny. So we kind of added one more new guy without having to add any new hardware. No new mux, just more control logic. Question? Yes, the only guy that does pay a little price, ain't no free lunch. You got to do a little bit more logic to handle that, and that's the next lecture, how to do control. But yes, there's a little bit more work to like, okay, another guy, what's the next row of how do we handle that? But that's it. That's pretty easy. And then again, write ALU output here, which is R of RS1 to the PC. All right, almost done, 5 minutes. The U types are only thing left. Remember, U types are like, 20 bits of upper. So I have 20 bits of a number to stuff into the upper values. So we call this the upper immediate, huge immediate. That's meant to be the upper 20 bits, not the lower 12, but the upper 20 bits. R of RD. So in this LUI or AUIPC, I've got an RD, which is the destination register for both of those guys. And I just said this, upper 20 bits. It's used in LUI and AUIPC. So the only thing that I see that needs to be changed is the ImGen guy. The bits are different, not the 12 bits that are the low side or moved around. It's the upper 20. So there's got to be a U type for the ImGen. That's all. What else? What's a semantic? That's it. That was it. I just changed the ImGen magically to do more like what we did before, and now it just works. Semantics are PC equals PC plus 4, R of RD equals immediate. Here we go. Stage 1, still in stage 1, read the new PC. Instruction, fetch it from IMEM. Now I know it's one of these two guys. I know it's a Louis. It's a new Louis case. Okay, I get to send. What do I do to do? I need to send some data. Look at what do I need to read? Or read nothing from the register file. R of RD means these 5 bits are setting up of what's the RD bits? These are the RD bits. These are the 5 bits of R of RD. That's why it's here. This 20 bits of immediate, wow, come in here. Now, see, this number's bigger, 31 to 7, more bits to the immediate. That ImGen gets all 32 bits for fun, but only needs here those 20 bits. ImGen is now set to U for upper immediate. Better do its work a little bit differently. It's pretty easy to do. You know that if we use the 20 bits, just drop them right in there. The lower bits are going to be 0. Reg write enable. Do I turn the reg write enable on? Look at the semantics. Am I writing to the register at the end of the day? Yes. Turns out 1. So all these are pretty easy to do once you kind of see it. Am I using a branch comparator? No. Put a star. How about B select? B select certainly matters because I need to select that from there. How about A select? This is weird. Look at this. A select. Show me the ALU operation. Let's go over here. Where's my ALU operation, anybody? And don't say plus 4 because that's already over here. ALU gets the rake. Hey, ALU, you're a really hard worker. Every instruction, you're working so hard. Take a break. Sit, rest your feet. What do you go? So ALU relaxes because I got to take this immediate and directly feed it into R of RD. How do you take that immediate red line and stuff into R of RD? I could do 2 things. One, I could add another mux and feed it around, okay? But remember I told the ALU to rest? Stop resting. Wouldn't it be cool if the ALU, who's already getting the B line, could ignore the A and just spit the B line in? So it still does a little work to make a decision, but ignores the A and just spits the B line out. So the ALU does do a little work, but not really. It's not doing any computation. It's literally taking the wires from B and just being the output. So it's not really work. It's just passing it in there. Now, it's combinational logic, so some part of that logic has to factor that in, and some mux internally does the right thing. Anyway, so now I have PC, now I just have the immediate. This cyan line is just the immediate. Do I have a path for immediate to R of RD? I do. I already have a path from the output of this line back into R of RD. So I just make sure that I set that right back is 1. Right back is 1. This right back selects as 1, which means take it from the cyan line in the middle. Because usually that's the immediate line, okay? So ALU kind of get to rest for a half a second, and its job is just to look at B and ignore A. So if it's ignoring A, what's the value of A select? Star. I don't even use it. I'm never selecting from A. Make sense? Pretty cool. Okay. AUI PC data path. Almost identical. Look at this. PC plus 4, that's easy, we got that already. R of RD equals PC plus immediate. We have that. We already have that active. PC plus immediate. It's U type. I got a PC coming in here. We already knew we had a PC coming in on the A guy. So here's my PC here on this very light green line. Here's my immediate coming in. It's still U type. ALU doesn't work. PC plus immediate. This MUX already has a wired path to go back into data W to be RD. Same thing. Fifth stage, write that back. Nothing. So like this is like, we're kind of getting bored, right? You're kind of like ho-hum, because this is mostly what we'd have to do. And in conclusion, ladies and gentlemen, let's do it. We have done it. Let's get applause. You're applauding yourselves because you're now, if someone said, hey, how could you build a risk file? I honestly think, how could you build, taking the SDS lectures and all the blocks you learned about that, which is like an ALU and a MUX and a memory box and a register file, could you